Imagine a place where the laws of physics as we know them cease to exist. A place of infinite density and unimaginable gravity. This is a singularity, the heart of a black hole. Singularities are the ultimate cosmic mysteries. These enigmatic points push our understanding of the universe to its absolute limit. They challenge our most fundamental theories about space, time, and the nature of reality itself. Singularities are born from the death throes of massive stars. When these stellar giants exhaust their fuel, they collapse under their own immense gravity. This creates a region of space-time so warped that nothing, not even light, can escape. This point of no return is called the event horizon. It marks the boundary of the black hole. At the singularity, gravity becomes infinitely strong. All matter is crushed into an infinitely small point. Imagine a star, much larger than our sun, nearing the end of its life. It has burned through all its fuel, and gravity pulls it inward. The star collapses, its core compressing under immense pressure. This runaway collapse leads to a singularity. The outer layers explode in a supernova, seeding the cosmos. The core becomes a singularity, the heart of a black hole. As the dying star collapses into a singularity, its gravitational pull becomes so strong that it warps the fabric of space-time around it. This creates a region from which nothing, not even light, can escape. This region is known as the event horizon. Once something crosses the event horizon, it's destined to fall into the singularity, forever trapped by the black hole's immense gravity. The more massive the black hole, the larger its event horizon, and the greater its reach into the surrounding space. The singularity itself, hidden deep within the event horizon, remains one of the most mysterious and perplexing objects in the universe. Our current laws of physics break down at the singularity, unable to describe the conditions of infinite density and gravity. We can observe the effects of black holes, from the orbits of stars to the powerful jets of energy emitted from their accretion disks. But the singularity itself remains hidden behind the veil of the event horizon, its true nature shrouded in mystery. Some physicists believe that singularities might not be points of infinite density after all. However, without a complete theory of quantum gravity, the true nature of singularities will likely remain an enigma. Imagine approaching a black hole, drawn in by its immense gravitational pull. As you get closer, you'd notice that space itself is being distorted, warped by the black hole's incredible mass. This warping of space-time is one of the most mind-bending consequences of Einstein's theory of general relativity. Near a black hole, this curvature becomes so extreme that it creates a kind of gravitational well, a cosmic abyss from which nothing can escape. Light itself, which normally travels in straight lines, is bent and distorted as it passes close to a black hole, creating strange visual effects. As you venture even closer to the black hole, the gravitational gradient across your body would become increasingly extreme. The gravitational pull on your feet would be significantly stronger than the pull on your head. This difference in gravitational force, known as tidal force, would have a rather unpleasant effect on you. You would begin to stretch, like spaghetti being pulled from both ends. This process, aptly nicknamed spaghettification, is a consequence of the extreme tidal forces near a black hole. As you fall further in, the stretching would become more and more severe, eventually ripping you apart at the molecular level. One of the most profound and counterintuitive consequences of general relativity is the idea that time itself is not absolute, but rather is relative to the observer's reference frame. This means that time can be affected by gravity, and near a black hole, this effect becomes extreme. As you approach the event horizon of a black hole, time would slow down for you relative to an observer at a safe distance. This effect, known as gravitational time dilation, is a direct consequence of the warping of space-time by the black hole's gravity. If you were able to observe a clock falling into a black hole, you would see its ticking slow down as it approached the event horizon, eventually appearing to stop altogether. From the perspective of the clock itself, however, time would continue to flow normally. For centuries, black holes were merely theoretical constructs, predicted by Einstein's equations but never directly observed. Then, in 2019, a team of astronomers using the Event Horizon Telescope achieved a groundbreaking feat. They captured the first ever image of a black hole. This remarkable image, showing a bright ring of light surrounding the dark silhouette of the event horizon, provided the most compelling evidence yet for the existence of black holes. The black hole in question, located at the center of the galaxy M87, is a supermassive giant, millions of times more massive than our Sun. Its image confirmed many predictions of general relativity, including the size and shape of the event horizon. Einstein's theory of general relativity predicted that massive objects such as black holes should create ripples in the fabric of space-time as they move through the universe. These ripples, known as gravitational waves, were first detected in 2015 by the Laser Interferometer Gravitational Wave Observatory, or LIGO. Gravitational waves provide a completely new way to observe the universe, allowing us to study objects and events that are invisible to traditional telescopes. Since then, LIGO and other gravitational wave detectors have observed numerous mergers of black holes, providing further confirmation of Einstein's theory and revealing details about the population of black holes in the universe. Despite these incredible advances in our understanding of black holes, many mysteries remain. The nature of the singularity itself, hidden behind the event horizon, is still a subject of intense debate and speculation. Some physicists believe that quantum effects might prevent the complete collapse of matter into a singularity, while others propose that black holes might be gateways to other universes or even entirely new states of matter. The study of black holes pushes the boundaries of our knowledge and imagination, forcing us to confront the limits of our current understanding of the universe. Our journey into the heart of singularities takes us now to the most profound mystery of all, the origin of the universe itself. The Big Bang Theory, our best model for the early universe, posits that everything we observe today originated from an extremely hot, dense state roughly 13.8 billion years ago. This primordial state, often described as a singularity, represents a point in time where our current understanding of physics breaks down. At the Big Bang singularity, all of the matter and energy in the observable universe were compressed into an infinitesimally small region. This concept is incredibly difficult to grasp, as it implies a moment when space and time as we know them did not yet exist. Our current theory simply cannot describe the conditions of the universe at that moment. The Big Bang singularity presents a fundamental challenge to our understanding of the universe. Einstein's theory of general relativity, which successfully describes gravity on large scales, breaks down at the singularity. This is because general relativity doesn't incorporate the principles of quantum mechanics, which govern the behavior of matter and energy at extremely small scales. To fully comprehend the Big Bang singularity, we need a new theory, a theory of quantum gravity, that can unify these two pillars of modern physics. Such a theory would need to describe the behavior of gravity at the quantum level, where the very fabric of space-time is thought to fluctuate wildly. Developing a complete theory of quantum gravity is one of the greatest challenges in modern physics. The idea that the universe could arise from a singularity, a point of infinite density, raises profound philosophical questions. If the universe began from a point of zero size and infinite density, what existed before the Big Bang? Where did all the matter and energy come from? Some physicists speculate that the Big Bang singularity was not actually the beginning of everything, but rather a transition point from a previous phase of the universe. Others propose that the universe could have emerged from a quantum fluctuation, a random fluctuation of energy in a pre-existing quantum vacuum. These ideas are highly speculative, and we currently lack the observational evidence to test them. The existence of singularities, both at the heart of black holes and at the beginning of the universe, exposes the limitations of our current understanding of physics. General relativity, our most successful theory of gravity, breaks down at these points of infinite density, unable to describe what happens within them. This breakdown has driven physicists to seek new theoretical frameworks that can reconcile general relativity with quantum mechanics, the other pillar of modern physics. One such framework is string theory, which proposes that the fundamental building blocks of the universe are not point-like particles, but rather tiny, vibrating strings. String theory suggests that the different types of particles and forces we observe are simply different vibrational modes of these fundamental strings. Another promising approach to quantum gravity is loop quantum gravity. This theory suggests that space-time itself is not continuous, but rather is made up of discrete, indivisible chunks, much like the pixels on a computer screen. These chunks, or loops of space-time, are thought to be incredibly small, far smaller than anything we can currently observe. According to loop quantum gravity, these loops prevent the complete collapse of matter into a singularity. Instead of a point of infinite density, loop quantum gravity predicts that the center of a black hole would be a region of extremely high but finite density. While most singularities are thought to be hidden behind event horizons, some physicists believe that naked singularities, singularities without event horizons, might exist. These naked singularities would be directly observable, potentially offering a glimpse into the unknown physics at the heart of these extreme objects. The existence of naked singularities is still highly speculative, and some physicists believe that they are forbidden by nature. The cosmic censorship hypothesis proposes that all singularities are clothed by event horizons, preventing their strangeness from affecting the rest of the universe. However, if naked singularities do exist, they would represent a major challenge to our understanding of physics. They could potentially violate causality, the principle that cause always precedes effect, and could even allow for time travel. Singularities, despite their enigmatic nature, offer a unique opportunity to probe the fundamental laws of physics. They represent extreme environments where our current theories break down, hinting at the existence of new physics yet to be discovered. As we continue to develop more powerful telescopes and refine our theoretical models, we can expect to learn more about these fascinating objects. The study of singularities has the potential to revolutionize our understanding of the universe and our place within it. Singularities stand as the ultimate cosmic enigmas, pushing the boundaries of human comprehension. They are the cosmic abysses where our current laws of physics crumble. Points of infinite density, shrouded in darkness, challenge our understanding of space, time, and reality. Within these enigmatic points, we find seeds of profound scientific inquiry. Singularities beckon us to explore quantum gravity, where macroscopic and microscopic realms intertwine. Though our understanding remains incomplete, their lure lies in the profound mysteries they hold. As we explore the universe, singularities captivate our imaginations, reminding us of the vast unknown.